So let's go on with the second part of today's lecture. And so now how to go on with this analysis. And you saw before you had a more acquisition-oriented way, but now we're going a little bit into a machine learning approach, how to analyze this effect of the thresholds. And we have one example from electron microscopy, where we have this image of some cells or a fraction of a cell, where you can see the mitochondria. And now we want to identify which class each pixel belongs to. And now is the question, what is this identify mean? So what we want to do is to identify the oops, I need to activate the pen. So these pieces here as foreground and all that here as background. In this example, I can actually see that there is something going on along the edge here. That's bad image quality actually, and it's not meant to be. But anyway, let's look into this. How can we quantify how good we have done? So there are different sides of it. We have the true positives and we have the true negatives, which is actually the pixels that are correctly classified as foreground and background. Then we have the false positive, which is values outside of the mitochondria that are classified actually as a foreground. So these are white dots spread around in the image, and it doesn't help us very much. The false negatives are like black holes within the mitochondria, which should be solid. And here we can see what happens if we apply a threshold 0.52 to this image. In the histogram, it kind of makes sense to put it here. Maybe you would like to put it over here instead. But now it's a question of the balance between how much you do misclassification and not. And when we apply this threshold at 0.52, we get this image here. So it's not really convincing. So we can actually get rid of some background, but not really all what we want. And this is actually what we want to see. So it's far from the truth of what we want to see. And let's do some counting. We can use sum functions. And first we look at the true negatives. We can see that there is good 100,000 true negatives, true positives, 13,000 about. You can see also that within them, there's a lot of black spots. So meaning we have a couple of false negatives, and then those you can see in this one. So there's also quite a collection of those. The big bad one is actually the false positives. So we actually say that there is a lot more structures that should be mitochondria, but they are not actually. So all this connecting tissue membranes, they actually also are classified as mitochondria, even though they are not. We can look back into the confusion matrix, and then I have decorated a little bit nicely, so you can see a little bit how much the different categories are represented. You can see that there is 60% is negative, true negative, and there is about 7% true positive. There is also 1.5% false false negatives, sorry. And this one is really an unbalanced part. And you can see here in this heat map where you have all the false positives. You can see in here some of these false negatives. All these ones are some kind of visualization artifacts. They hadn't appeared before, so I don't really know why they appeared. But anyway, the main thing is that we have a lot of pink, which we don't want. We also have some blue within the mitochondria, and all that gives us an indication of how good we have segmented this data. You can also see here that there's a big imbalance between false negatives and false positives, meaning we are doing clearly telling that there is a lot more mitochondria than there should be. Ideally, you should push both of these to as small values as possible. The ratio between those two could be true that they actually are like this. You can have different representation of the different features in the image, and you can actually truly see that there are not so many mitochondria within this image, so it's natural that this one is much smaller. Most of this should actually move over here, so we have nearly 90%, should actually have nearly 90% as background. So this gives us a quick overview of how good our segmentation is. Other metrics we can use are precision and recall. Recall tells how sensitive our measurement is, and it's the ratio between the true positives that we actually have seen divided by the true positives plus the false negatives. That means this one is all that should belong, all truths, all that should belong to the class itself. But some of them we missed because of the false negatives. The precision is almost the same, but now we look at false positives here instead. So it's actually all the pink plus the white, and that would be the white plus the blue in the previous figure. You can, in principle, have, you should aim at having a 1 here and also here, but usually you don't get it. And a way to look at this is to use, so you can see here that we can calculate, we have a recall of 82, a 0.82, and a precision of 18%. And well, of course, if you looked at how much pink we had in the image, it's clear our precision, we are telling more or less everything is mitochondria, which is not. So our precision is pretty bad in this case, even though we can say also, we actually collected all the mitochondria pretty well. So it's a balancing between those two. A way to analyze the performance of a segmentation method is to use something called Roc curve, or receiver operating characteristics. And that is something that was in the beginning used in detection theory and looking at radar images or radar screens, telling here we have something, an airplane or something, and here we don't. And in these radar images, there's a lot of clutter. So you see maybe reflections from trees, etc., and those may be misinterpreted as airplanes. Now we just looked at a single threshold, but we can compute from that. We can compute recall and precision, but now we want to do some kind of scan and look at what happens when we set different thresholds. And for that, there's a little bit of code, but the important thing is that this code produces this table. And for different thresholds, so here I'm scanning the different thresholds and can compute recall, precision, false positive rates, and also true negatives, false positives, and so on. And now let's look at the plot of this. But first, let's just a little bit look at this how this plot is shaped. that is not so smart. Let's put that one in upper right. So you can see here we have a plus at 1, 0. This would be the ideal thing, that we have all is true positive and there is no false positives. So what you see here in this ROC curve is the relation between true positives and false positives. Our measurement produced a dot over here. Single dots is not much exciting to look at. So what we need to do is actually to use the table we created a couple of slides ago and plot and see what happens here. And now you can see that we have, if we set a very low threshold, we have no false positives, but also no true positives. So it's a really bad condition here. And then when we increase the thresholds, we can see that, well, somewhere around here, oops, I need to activate the pen again. Somewhere around here, we probably have a good balance between false positives and true positives. But the exact decision depends on what you need to do. So sometimes you can accept more false positives. In other case, you really want to be sure that you get all the data. So it's really a balance or a decision you have to make, which balance you want to work with. So we can also see what happens if we apply different filters. So coming back to the some of the filters we used in the filter lecture before. One is, so we have the first, the original, and then we have applying a Gauss filter. You can see that the noise has been reduced, but also that the edges are a bit blurrier. This one is the difference of a Gaussian. So you have the image minus a Gaussian filtered image, and that produces a high pass. And you can see that now you get a lot of these edges are enhanced, but maybe it's not really what you would need, but we take it in here to see how it behaves. And then we have the medium filter, which also does some noise reduction. And what that looks like is we get some new curves. We have the blue curve here and see that, well, it performed somewhat good. If we look at the Gauss filter, you can see that we have a much better true positive rate compared to the false positive rate. Median is somewhere in between, and that is to be expected. I think the filter kernel is actually wider here. So it actually covers larger neighborhood, and thereby it also does a better noise reduction effect. This difference of Gaussian, that one is a strange one, actually is just to show that you can do the wrong filtering too. So in some cases, it's even worse than random guessing. And then there is sometimes, mostly it goes above, but you can still see that the original image is better than the difference of Gaussian. So this one was just to show that you can do the wrong filtering too. These curves, you can only do some kind of qualitative assessment about if you just look at them. So instead, we want to put scalars on it and measure how good it is. And one metric that is used on the ROC curve is the area under the curve. So what it does is actually to compute this area, and that is the value that we are putting in here. And you can see, as we expected, that the yellow one, which is the Gaussian, actually has the largest area under the curve, which is in that case the best choice of filtering compared to also to the no filtered. So the improvement of adding a medium filter compared to Gaussian is no, mid-infinity compared to original is limited, but it also depends on which kind of filter kernel size you are using. So here you can see some effects of using filters on the segmentation result. Well, sometimes it's not enough just to say black or white, and that's actually very often the case, that you need to identify different things, and that is when we go into segmenting multiple phases. And here you can see a multi-phase example. We have some rock sample where we have void, clay, and rock are the classes we want to identify. Looks, yeah, well, not too easy, I would say, but let's try doing something about it. First thing we do is take a look at the histogram and identifying where we have our different classes. You can see here in the data, you have bright spots, you have some grayish in here, and you have some dark. It's very noisy image, and I would say you have the bright ones, which is the rock, the most dense. Then you have the clay material, and you have somewhere around here, you have some air as well. So let's try setting up some thresholds on this. Now I have chosen saying that the void is everything below 0.3. The clay is everything between 0.3 and 0.5, and the rock is the rest. And then we can put our threshold in the histogram, and, well, kind of makes sense from what I was drawing in the previous one. And now when we apply this, we can see that we have the image and the voids, well, kind of makes sense here to put the thresholds like this. You also have the clay, which is all the white. Thinking back about the histogram, it also makes sense. We have this large mode in the middle, and then the rock are only the bright pieces in here. And qualitatively, I think this is a good segmentation. Probably needs to be done more, but it's a good starting point. Now we have been talking about how to implement this. Talking about how to use the threshold, but implementing it is also something that needs to be done. And in Python, we already saw how to do it. It's a very simple task, actually. You can do something like this. Just say you have the gray level image, which is greater than the threshold. You have your segmentation. Fantastic. If you want to do something more complicated, you can also do combinations using these Boolean operators. I can also use the OR if that makes sense to you. So here you can say that if gray image is greater than the threshold and gray image is less than the other threshold, then you can limit down into a band of gray levels. So if you would have something like this, you can say here, this would be threshold A, and this would be threshold B, and then you would get all the pixels in between here. So this is the way you do it in NumPy with Python and with MATLAB. If you would do it with Python without NumPy, then you would have to use some kind of mapping function and a lambda function, a little bit more complicated. So I would suggest actually to use the NumPy, because usually when you're working with images, you anyway have NumPy loaded. Then if you go into more the traditional programming languages and look how you would do it here in Java and C++, it's almost the same way of doing it, but a little bit more about the implementation of how you allocate memory. So the first step is you need to allocate memory for the data. And then you go through different loops, and you have one loop for the x coordinates, one for the y coordinates, and one for the z coordinates. Then you need to locate the position in the image. Computing it here, we have different dimensions to work with. And then finally you get some offset. And then you apply the threshold to this offset, to this position in the image. Same goes also for C++, where you also do some memory allocation. I would maybe rather recommend using the new here, but if you do it in the really true old style C, then you would use malloc. This would be the C++ way. But as you can see here, you have 3 loops and you compute an offset. So instead, you can actually just do a single loop as I'm doing here. And then it would be just for I equal to 0 and I less than number of pixels, and then do it on the image. So the image I is equal to img, oops, I is greater than threshold. So something like that. And that would reduce a lot of complexity, and that makes it much more efficient to implement. Maybe not so explicit in what is actually happening, but it's more efficient for the computer to work with. Now we have got our images segmented, and as you have seen already, there is usually quite some misclassifications in the data. And we want to remove that. And one way of doing it, except for improving the segmentation method, is to use morphological operations. And these can help you to clean up the images. And it's a kind of filter looking at the structures in the image, or structure matching. And well, noisy segmentation can look really bad. You can see here the cross is not looking very well. Barely visible, that's the cross. And this we want to improve. And for doing that, we can look at all the surrounding pixels around each pixel. You can look in the neighborhood and see what is the more likely value of that pixel. You can use different neighborhoods. If you use a large one, you have more to look into, so it takes more time, but it can also remove more of the misclassifications. If you do a small neighborhood, of course, you can also reduce computation time, but you may not do such a good cleaning. So it's a balance. And I mean, also be careful when you do too large neighborhood, then you may also cancel relevant information. So that can be used for very many things, this kind of neighborhood. First thing is filtering. So also actually the normal convolution is using a neighborhood. Morphological operations, which we are going to talk about now. Component labeling and distance map is something we are going to talk about in some weeks. So this will come. So all the time we're looking at neighborhoods around the pixel you are looking at for the moment. And it's often called a structure element, this neighborhood. So in some cases it's called SLM in the functions. And looking at the different neighborhoods we have, for example, for 2D, we have 2 definitions. We have a 4 connected neighborhood and an 8 connected. And what it means is that you have this central pixel and it has 4 neighbors in the vertical and horizontal directions. The 8 connected adds another 4 neighbors. So that would also cover the diagonal corners. And depending on how you select this neighborhood, First of all, you have a speed difference because you have half the comparisons if you use a 4 connected compared to an 8 connected, but also the kind of structures that you can get are different. So here are also some more neighborhood shapes. You can use pretty many different. It depends on also what information you want to highlight. And here you can see disk, across, just a horizontal line with different thicknesses, a vertical line, a star, octagon. So you can use different definitions. And actually, the disk, star, and octagon are different kinds of definitions of a discrete circle, depending on which radius you're using. But it also gives some more detailed shape names in this case. If you go in 3D, you have to actually extend with 1 dimension. So instead of 4 connected, you could have a 6 connected or 27 connected. Then there is also one called, let's see, 18 connected. Then you would fill in with all these. I'm not drawing all of them, but it would be something like this. Yeah, something like that. So that would actually just leave out the 3-dimensional diagonals. So that's also one that sometimes is used, but 6 and 27 are the typical. The typical operations you do, or the very basic operations you do when you have work with morphology, is erosion and dilation. And what erosion does is shrinks the image. So if any of the voxels in the neighborhood of the one you're looking at is 0, then that pixel is set to be 0. Dilation is the reverse, doing if any of the pixels or voxels in the neighborhood is 1, then also the center pixel is set to 1. So it's a kind of these operations kind of a search and replace functions, you could say. So you would actually have like coating something with extra layer. Looking at them, first just what the effect is. So we have in the middle, I have the original image, and applying the erosion to it, you can see that almost everything is gone. It erodes a lot because I have a lot of thin structures here. Dilation does the other thing. It actually makes it grow bigger. So what is actually happening here? If I have a structure element here, I actually didn't show it, but yeah, up here, you have the structure element, and it's actually this 4 connected neighborhood is our structure element with the center point. So if I put this neighborhood on this spot here, that would be this one, then you can see that it actually hits, and we get that pixel is clearly set to be 1. If I'm standing on this position and add, then you can see again, yes, there is actually also a good hit. So this one is also growing. So the effect of the dilation, you can see here, it's growing out like this. So actually here it hits 1, and that makes this one to be drawn as a 1. So, and if I would stand over here, no, let's take it somewhere else. If I would stand over here and I'm putting the cross in here, you see there is nothing that that touches the original image, and therefore this one is also drawn as a 0. And erosion does the opposite. So here it's required that the whole cross is within the image. And for example, if I'm standing here on this position, you can see that the whole cross is in. And that's why we get a yellow pixel here. If you would stand somewhere along at the edge, somewhere around here, this pixel, then you can see that there is a lot of pixels going outside, and that's why this pixel is erased. And this is done then for each pixel, and you can see here that it's shrinking a lot because I have so many thin structures in this image. This is maybe good, but as you can see, you change the shape pretty much. And you don't want that always. You want actually to keep the original structure as much as possible. And then if you would combine the two of them, then you get two new operations called opening and closing. So opening is an erosion followed by a dilation with the same structure element. And the effect of that, and then you have the closing, which is dilation first, so you grow, and then you erode again. So, and the effect is that if you do a closing, you can see here that the structure that you lose, that all these gaps here are closed. This one is also closed, and this one is also closed. But if you would have instead have an opening, then you would remove structures like this, that, and so on. You can see then you have some kind of Space Invader ghost or something left over. And this goes, of course, in two steps. So the closing operation, then you apply the dilation first. You can see the dilation as the little bit darker blue, also mid blue, is the effect of the dilation. And then in the end, the green ones are the ones that are filled out after that remains after the erosion from this structure. So it's first growing out, and then it's shrinking as much as it can from the grown image. And then you have these closed bridges here and here, and also the holes over here. So this is an operation that is very useful if you want to remove false negatives in the image. The other one is the opening, and then you first do the erosion, leaving us with only these yellow dots, yellow pixels, and then those are again dilated, and then you get this green area. And as you can see, you remove a lot of information all over the image. And finally, you get this. The purpose of the opening is if you have false positives, then you can remove them, because the false positives are usually just mostly just single pixels or few pixels that you want to remove. Thinking back on the mitochondria example, it would probably require quite a large structure element to clean, but it would still work. Now, the last part of today's lecture is problems when you do segmentation, and that is partial volume effect. And the image is only defined on a discrete grid. And in some cases, when you're close to the edges, it may be that the captured intensity is not as strong as in the middle of the object. So you have some kind of slope along the edges. And that depends on how well resolved the image is, and also from the resolution of the imaging system. And when you try to segment images like that, it can give different results. So one thing is, if you have very small items, it's difficult actually to draw an image which corresponds to the shape that you actually want to see. So here in this example, I have created circles with different number of pixels. So the side length is what you see here. So this image has 10 pixels side length, 20, 50, 100, and 500. And you can see that this circle, in this case, more looks like a square. And now it looks, circly. like, but here it starts looking like a circle. And the more pixels you use to define the object, the more exact you can define how the shape of the object. And that's important to know, that you need a certain amount of pixels if you want to segment it and still have a true shape defined. This can also be used in 3D. So here is the case of a very small sphere. It looks like this three-dimensional cross. Some sphere at, I think it was radius 3 or something. And here is radius 8, I believe it was. No, it's less, 5, 6, something like that. And you can see that the more pixels we have to define the object, the more it looks like what we expect it to. And then I did this volume error analysis where I looked at the volume of the discrete sphere and divided it by the analytical sphere. So looking at the equation of how you compute a sphere for a given radius. And then you can see that you need about 10 pixels radius in order to have a volume error of about 1%. So you need to have a certain size in order to draw an object correctly. And then, of course, you can go on with more and more. And this was only for a sphere. If you have a more complicated object, it's even more difficult. So you have to be aware when you do segmentation that there are errors involved in the volume measurements or in the surface measurements of the object. Another problem is if you start scaling the data. So if you start doing having a large image, you downscale it from 500 pixels to 34 pixels. You can see that, well, it does something, but there are some gray levels here. And this is an effect of when you do downscaling of the segmented data. And you can always get these gray levels on different places. And you can see that there is a step in between, and it should actually be a discrete step from white to black. But with the downsampling, depending on how you do it, which kind of sample you use, you can get some intermediate gray levels, and they can be pretty annoying when you continue doing your analysis. And that brings us to the end of today's lecture. Today, we have been looking at how images are formed and how that then later relates to the segmentation problem, and also how difficult it can be to identify what is actually we are seeing. Then we looked into how to evaluate how a segmentation method is working, using hit and miss counts, using the Roc curve, also a confusion matrix. The images, as we could see, are not always so nicely segmented. So for that, we need to have some kind of cleanup ways, and morphological image processing is a good way to clean up the image data. The final part of today's lecture was that we also looked into some problems and things to think about when you start doing segmentation, and in particular at the effect of partial volume, that not the whole pixel is belonging to the object. And well, that was all for today, and thank you for listening. Again, I would like to take some minutes off, and then we can look into the exercises.